Hello. Hello, check. Hello, 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 check. Hello, hello, check. Hello, hello. Hello, 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 check. Hello, 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 check. Hello, 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 check. Hello, 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 check. Hello, Hello. Check. Hello. 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 Check.
Adam, bootstrapping a deep NN-based sequence labeling model with minimal labeling, solving vehicle routing problem for optimizing shipment delivery. Check, check, check. Podium is, it is inclined. Sulfur, bit more. Almost. Okay, ಅಮ್ಮು ಇಲ್ಲಿ ಒಂದ್ಸತಿ ಹೇಳ್ಬಿಡು ಇದು.
Hello, hello, check. Hello, hello, ಇಲ್ಲ ಇಲ್ಲ. This is 1 9. Hello, 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 check.
Hello, check, 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 check. Check, check.
Hello. Uh, okay. Hello, I'm Shashank Jaswal, and I'm here presenting Adam for fifth event. Clear? Thank you.
you speak now?
A very good morning to everyone present here. I'm Harshita, your hall manager for today. Today in the auditorium 2, we have a talk which is followed by a tutorial, and then we have a break. Later we have a talk again which will be followed by a tutorial. Post lunch we have a tutorial, after which we have BOF sessions and flash talks. We have a few announcements. Kindly turn off your phones or put them on silent mode because we do not want phones ringing and disturbing participants or speakers. And we have Wi-Fi available by the name Hasgeek, and the password is GEEKSRUS. GEEKSRUS. And we have food court available, which is next to the auditorium 1. And we have flash talks in auditorium 2, which is here, from 4:55 p.m. to 5:30 p.m. and we have 7 slots, each of 5 minutes. The flash talks, we need presentations without any laptops. It is going to happen by the participants, right? So the laptops are not allowed. If the laptops are only allowed if you have a demo to show. If not, the laptops are not allowed. And no hiring or any production pitches during the flash talks. And if you are ready to give a flash talk, then you can write your flash talk topic with your name and phone number on a slip of paper and hand it over to the hall manager, that is me, right? So if you are interested in giving a flash talk, you can write the topic, your name, your phone number in a slip, and you can hand it over to me. And we have a Redis AI tutorial in auditorium 2 starting at 1:55 p.m. So make sure you have installed the software required for attending the tutorial. And we have BOF sessions running in auditorium 2 and auditorium 1. Please check the schedule which is given to you during the registrations. And yeah, that's pretty much it. So now we have a talk, the first talk for the day, by Shashank Jaiswal on Adam, bootstrapping a deep NN-based sequence labeling model with minimal labeling. Thank you.
Hey everyone, so I am Shashank Jaiswal. I am a data scientist at Cluster, and I'll be presenting here Adam for Fifth Elephant. So Adam stands for Attribute Detection and Annotation Module, which is just a fancy name for named entity recognition. Now we pitched this name because we also had an Eve project coming up at our company, so well, you can understand why. Interestingly, we are also the first talk here at Fifth Elephant, so coincidence? Maybe. So as I said earlier, Adam is an advanced named entity recognition module for domain-specific data designed specifically to deal with the absence of label data. It leverages concepts from weak labeling to deep sequence models and the concept of active learning. So to understand anything what Adam does and how it is formed, let's first understand what named entity recognition is. So in a very layman term, if I speak, it's just actually picking out important stuff from a sentence, like a name of a person, or the position, or an organization. Or it can mean something really different in different domain. For example, in hospital records, symptoms, diagnosis, or diseases can form named entities. Now imagine you are trying to make an algorithm or develop an algorithm which can predict some diagnosis given some symptoms. You can imagine the importance of such tools like Adam in that domain. Similarly, for product descriptions, they play a very important role in e-commerce and other businesses like these because they are loaded with attributes which are used to enhance search and semantic abilities in various product catalogs that you see. So attributes like brand name or the category of the product, and various other specs like nutrients, for example, in this case. So similarly, what will Adam do? Adam is basically, as I said earlier, it's an advanced named entity recognition module. It will do exactly the same thing, which for the examples that I showed earlier, but it will do that for product titles like this. I picked this one because you might be a little more interested for this. So we at Cluster are associated with Tally. As many of you might know, is an accounting software. Now, we get our data from millions of businesses here in mostly small and medium enterprises, which are present here in India and select other countries. So one of the data that Tally stores is actually inventory, which is required for bookkeeping. So what that inventory is formed of is each unit data that is present in inventory are these stock items. So what will Adam do? Just pass these stock items to Adam, and it will resolve them. We use a standard BIO tagging method to extract elements from stock items. So you can see that the tokens Resolute and Black are tagged as BB and IB, which means beginning and intermediate of the brand. The word vodka is tagged as BC, which means beginning of a category. And similarly, you cannot see here, but 180 ml was tagged as O, which means others or non-relevant attributes. So that is the whole objective of Adam. This is what Adam will do. Now, why is it important? Why is a module like named entity recognition important in product titles domain and the domain in a business domain? So there are several use cases. One is universal product catalog. So you often see product catalogs in websites like Amazon or Flipkart, or even specific retailers like Big Basket. Now these product catalogs have enhanced capabilities where you can filter your search depending on your attributes. You can filter your search based on the name of the brand or other specs like whether you want your earphones to be wired or wireless. So you can understand the importance of these attributes in a catalog. Now imagine if you have a way to extract these attributes from the product title itself, you can actually automate the whole enhanced semantic search that is present in these catalogs. Similarly, aggregation and market analysis, lift insight, demand insight, popularity of a brand in a given location, penetration of a brand in a given market, or competition for any certain category of a product, price distribution, etc. All these insights can be heavily impacted by a module like Adam. Third is knowledge graphs. So knowledge graphs are formed using the named entities that are present in product title or some other data source and the relationship between them. So all the nodes in a knowledge graph are actually formed using the named entities. And the edges between these nodes represent some kind of relationship between them. So if you can extract these named entities from various data set that you have, you can actually have a breathing, evolving knowledge graph, which can consume the data set automatically and can grow. So, and clearly, we were not the first one to think of this. There have been many previous approaches to this. Traditionally, people have used CRF algorithm with handcrafted features, or have used a healthy knowledge base like DBpedia or Wikipedia, etc., to do these exact same thing. For example, one of the paper in Walmart Labs is by Ajinkya More, who tried to extract the attributes, specifically brand, from the product titles of products present in their Walmart's catalog. So here's one of the example of the handcrafted features that they used. So they use a feature like the word itself, lemmatization of that word, neighboring words, whether the word is alphanumeric or not, and some features like these, which were chosen to extract attributes from product titles. And you can see that it actually worked really well for them. So this is one of the examples that you can see, and they were able to extract brand from that pretty nicely. But when we tried it on our data set, it was a disaster. The reason being, our data is extremely variant. It's acquired from millions of sources, and there is no check between how do you write a stock item or how do you write a product title. So the problem is it couldn't perform very well on our data set that we had. Although it worked really well for very famous products like Maggie and wheat, etc. And there are some other works like, there are many off-the-shelf tools, like the very famous one is Stanford's NLTK, which is just like a plug and play. You can directly download the resources and start playing with it. But the problem is they were trained on natural languages, languages which have proper grammar in it. So, for example, here one of the sentences, Barack Obama is the next president. It's a pretty old sentence, but it will do. And you can see that it extracted the name of the person and organization pretty well. But the problem is these attributes were not required by us. These are very irrelevant attributes to us. And you can see in the next example, it basically was really poor. Everything was tagged as noun, and it couldn't actually differentiate between anything. So that's why you couldn't use any off-the-shelf tools. Then comes the state of the art, paper by Lampel and Zuzma, and there were many other names that I couldn't pronounce. So these people have worked on really complicated neural network architectures, including BiLSTM, CNN, and CRF, to produce an accuracy for such tasks close to 90 to 95%, which is amazing in this field. Deep learning has actually taken a big leap from traditional algorithms. But the problem with them is they either required a large label data set, like the paper by Lampel and Zuzma. They showed that they required around millions of sentences to reach convergence. But so that wasn't the case with us. That is not the case with most of the industrial data that is present there, specifically in textual area. So, and other papers who claims that they have done it in a very less amount of data set are very domain specific. Like they have a very narrow segment. For example, the paper here by OpenTag was actually, they showed their result only on specific segment like dog foods, which you can understand how narrow that segment is. And the problem is we didn't have that information. We don't have a data segmented already so that we can work on them. So we had to think of something else. Also, there are some additional challenges that were taken care of in any previous paper. So because, as I said earlier, we get our data from multiple sources, so there is a lot of variance in our data set. For example, this is a proper written stock item, which is very easy to understand. This one, not so much. Here, N actually stands for Nivea, and talc is actually full form, it's short for talcum. But okay, it's still workable. This one is horrible. It's not the BMW that you guys are thinking of. It actually stands for Bisleri mineral water, which we could understood only because we found out who was the retailer of the stock item, who actually holds the stock item. That's how we actually got to understand that. And then there are some other problems, like the data set is extremely noisy, the spelling of sun drop and heart is terrible here. So these are the problems that we had to face. And that's why any traditional approach couldn't scale, and all the state of the art required a large amount of data set that we didn't have. And please note that BMW is actually written in red because we don't claim that we can solve them by today. So here's what we need. We need a model that can predict tags relevant to our domain. Like, okay, for this session, we'll only focus on two attributes, brand and category. So we need something which can extract those. We need a model which can scale across various segments. We cannot have a model which can be very good in one of the segment and terrible at another segment. We need something which can scale across all the segments that we had. Then we are not claiming that we'll show some crazy unsupervised algorithm here that can predict attributes without supervised learning. So yeah, so there is a fact that we require some label data to work with. But what we are claiming is that we'll reach that point, we'll reach that maturity with the minimum amount of label data that is required. And there is actually a significant gap between the amount of data that we require to scale and the amount of data that is presented by many research papers. Also, we need an approach that can scale on streaming data. So that's a specific case for Tally. We'll not get all our data at once. We'll have a streaming batch system. So we needed an approach which can scale every time there's a new, every time a new batch arrives. It shouldn't happen that I need to take a big dump of sample from them and then get them manually labeled to scale, which could be really costly. And then the last point is pretty obvious. It is needed, obviously. Now let's take a deeper look at the architecture and the training process of Adam. So I have presented Adam as a data science problem till now. Now let me present Adam as a machine learning problem. You provide a sequence of input to Adam. Please focus on the word sequence. It actually, I think you can understand what here by sequence I mean, but please focus on that. That would be helpful in later slides. You just pass it to Adam, and what will Adam do? It will predict the tags corresponding to individual tokens here. This is pretty obvious. I think you can understand that. Moving forward, so here are the approach that we took to train and design Adam. It is actually divided into three crucial parts. The first one is weak label generation. So we had nothing to start with. We had actually zero label data. All the data that we had was unlabeled. But we had a small amount of knowledge base. So knowledge base consists of dictionaries of these attributes. Like we had some amount of brands. We have a few categories and other attributes like flavors and color, etc. So what we did is we used them, and then we took a lot of stock items and then used a complicated string matching algorithm to automatically label them. And they had to go through a quality check, after which we received something like this. So this quality check was necessary so that because there is a lot of ambiguity that was produced using this approach. For example, if let's say if Apple is present as one of the token, it can be tagged as both brand and category. So there were many ambiguity that was present, and this approach couldn't resolve them. That's why there is a quality check in between, which remove any result with such ambiguities. So we passed around 1 million such stock items through this approach, and only 8,000 were able to pass the quality check. You can understand how weak our knowledge base was to have this result. So we started with around 8,000 weakly labeled data set to moving forward with. Now let's talk about what goes inside Adam. How is its architecture? It comprises of, again, three crucial layers. First is word embedding layer. The second is bilesterum layer. The third is CRF layer. I'll explain these layers briefly in the next few slides. And this is what Adam is supposed to do. The first is word embedding layer. Now, for the people who are not familiar with the concept, word embedding layer is basically you project all the words in your vocabulary into an n-dimensional space where each word is assigned a specific coordinate. Now, this the relative spacing and the relative positioning between these words holds some semantic information in this n-dimensional space. And that is what word embedding layer tries to preserve. There's actually a very famous pre-trained word embedding set called Glove, which is made by Google, which was trained on millions of books, millions of sentences from various e-books or PDFs or whatever data they can get, like news articles, etc. But the problem is we couldn't use them. We couldn't use them, that mighty massive word embedding layer from them. The problem being the domain that we were working on is very different from the domain it was trained on. So most of the word that we had in our system was actually out of vocabulary for them. So we couldn't use them. Hence, we had to create our own. For that, the data set that we used is, we used all the stock items that we had in our first iteration. We added some product titles from publicly available catalogs like Amazon. Amazon actually provides you with all the catalog stock items that they have, so you can play with them. And then we partnered with some data providers like GS1. And so I wouldn't dig deep into what GS1 is. You can just understand that they provided us with 2 or 3 million stock items from specific segment, FMCG to be precise. So from that, we gathered around 13 million titles. And then we used a skipgram algorithm. Thankfully, that algorithm was unsupervised, so we could use all the data points that we had in an unlabeled manner. So, and I wouldn't dig deep into a skipgram algorithm earlier. I have cited that paper, and it would be present in the links of the proposal that I have. You can actually go through it. It's a great read. So here's one of the interesting insights. So I tried to project 128 dimensions into 2 dimensions so that you people can perceive it, but clearly we can't because, well, it's gibberish. But in the right side, yeah, sorry, left side. my left side. Anyways, so in the left side you can see that the word Samsung, if you search for the vector of the word Samsung, and then you see the nearest neighbors for them, it's actually Galaxy S3, S5, S6, which I think most of you here know is some variants of Samsung mobile phones. So you can see that the semantic, the position of these word embeddings do hold some semantic information, and we try to leverage them. Second comes the bilestim layer. So bilestim layer is another word level encoder which leverages the sequential information to encode the tokens of the sentence. Now, as I said earlier, you can imagine the tokens in sequential manner where first token arrives at t1 time steps, the second token arrives at t2 time step. So at any time step t, not only the input is that embedding of that token at time t, it's actually some context from past also. So as you can see in the diagram, some context is passed from previous time step at every time step. So this is how it tries to predict some output based on some previous context that was passed along. Now, why was this necessary? Why was this another word level encoder necessary after word embedding? So you can see two sentences here. Both of them are formed by a similar word, but only one of them makes sense and the other one not. If you look at second one, it's properly written. The brand name, the brand comes first, then the category, then unit of measurement, and the measurement itself, etc. But if you look at the first sentence, it's actually just a jumbled word of first form, and it starts making very less sense compared to the first one. So this is the information that LSTM can hold, which the only word embedding layer could not. And that's why bilestim layer was used to leverage it. Then comes the third layer, conditional random field. It's the old traditional CRF algorithm, but it's now fitted over top of two heavy neural network layers. So again, this is also a sequential algorithm which has similar concepts like bilestim layer. But it had one more advantage, and that's why we use them. It is the only layer that leverages the output label context. For example, the sequence of output should also matter. Bilestim layer was not taking care of that. But this layer does take care of that. For example, the I tag should never, so the O tag should never be succeeded by an I tag. There has to be a B tag in between. You can understand that. So this is how CRF exploits that information. So it tries to learn a transition matrix. Now what this transition matrix is all it does is tries to learn the cost of transitioning from one tag to another tag. Like for example, row 0, column 1 holds the transition cost from BB tag to IB tag, and similarly everything else. Now you can understand some of these costs should be really low. Like you'd often see IB tag to be succeeded by to be preceded by a BB tag, but it would be very it's actually it should never happen that an O tag is succeeded by an IB tag. There would be a BB tag, as I said earlier, would be in between. So some of these value would be really high, some of the cost would be really high, some of the cost would be really low. And this is how it gives the importance to the output context of the algorithm. Then comes a loss function. Now I understand people who are not from the mathematic background, this equation can seem really scary. Trust me, people who are from mathematics background and don't know about this, it can be scary for them too. So instead of directly jumping into this, I will first explain this with an example. So here you can see that in the bottom there a sequential input is given, and in the first column it's actually all the tags that are possible. Now each column that you see holds the value of probability of a certain token being a certain tag. For example, the probability of the token Maggie being BB is actually 0.80. The probability of noodles being BC tag is 0.71. And the scores above each arrow that you see is actually the probability of the transition. For example, the probability of transition from BB tag to BC tag, it's actually 0.7. So this is how you calculate the total energy that is required for a given input of stock item to attain a particular sequence of tags. So you can see how total energy is calculated. It's just the summation of log of probability values of all these probabilities. So, so for a particular sequence, you'll get a particular energy score. Now, ideally, what should happen for the correct tag, for the correct tag sequence, the value of energy should be really low, close to zero. It should be really low. The magnitude should be really low. And this is the loss. This is the basic loss function of the module. This is what the model tries to learn, tries to minimize for every correct sequence. And in this example, so this is basically what this loss function tries to extract. The energy equation that you saw is actually these summation values. So the the function here you see that is the function that generates those emission score, basically the probability score and transition score. And yeah, T is just for time, I is time step for something, and lambda is just a trainable hyperparameter. Now ZX is a normalization score here. It's actually so there can be, for any given input sequence, there can be length to the power n possible sequence output sequence possible. So this is so we try to normalize that score by summation of all these values, because see the output energy is dependent on the length of the sequence. So we try to we need a way to normalize that. Hence we used a normalization value. And this is a very standard process for any sequential algorithm. It's actually likelihood. This is how you calculate the likelihood. So that's what we used. Now here are some of the results. Now this is the result with only BiLSTM as final layer and not CRF layer. So without CRF layer, you can see that it still predicted okay-ish output. I mean, for example, in the first example, it's not wrong to say that ghee is actually category and bread is a brand. But when we use CRF layer, it actually, the smoothness increased. Cow ghee is actually more relatable category here. Similarly, Patanjali Kesh Kanti is the complete brand sequence. And something else. So that's why we used CRF layer at the end. Now, people who have worked in this domain can argue that BiLSTM, if you had used a thicker BiLSTM layer, it would have given me a similar result as with CRF. Yeah, and I wouldn't argue with them. They are absolutely correct about it. But the problem with that is, if you are using a thicker layer, you need more training data to reach same amount of result as with CRF. And that would deceive the whole point of what I'm trying to make, that of minimal labeling cost. Hence, we tried with CRF. So after doing all of this, here is some baseline result. So the accuracy of predicting brand specifically was 32%. For category, it was 36%. And for a complete sequence match, it was 22%, which I was saying is absolutely shit. So yeah, obviously we couldn't present this anywhere. And but it gave us something to start with. It gave us something to start the whole active learning process. Now, one limitation with our automated weak label generation processes is that it is constrained by the completeness and quality of knowledge base that we have, and we had a poor one. So from those, we were able to get only 8,000 weak label data set, and then we estimated the set at least which was required to achieve convergence, which was around 1 to 2 lakh, or even more for only the first iteration of data points that we had. So, and not only that, we needed an architecture that can iteratively scale for streaming data, as I made my point earlier. We need an architecture that can scale with new data coming in. So our labeling cost had to be minimized to achieve scalability. So here's what we did. Now, this is what we are left with after the first two approaches. We had a small amount of labeled data set from weak label generation. We had an abundant amount of unlabeled data set. And we had a deep neural network module trained for us. So what we did is, using all the three, we developed an extrinsic sampling algorithm which can sample a small amount of data points from unlabeled data set. So, and the sample data set that is extracted here is actually semantically very different from the label data set that we had already. So, so when we manually label them, use it again to retrain the model, what will happen? The increase in model's accuracy would be very much better than if would be much better, because the data, the new sample data is not redundant to the label data which was already present. So that is the aim of active learning. You choose your sample consciously for every iteration, so that with minimum amount of label data, minimum amount of new label data, you can achieve high accuracy jumps. So this is what we did for few iteration until your model reach a certain maturity. It can be some threshold percentage. Or you can see that after sometimes there wouldn't be so much growth in your accuracies. So now this block, this extrinsic sampling is something novel, and we tried it for the first time. It hasn't been tried before. So what we did, we had a list of all the data points that we had. Now, the first aim was to project them in an n-dimensional space again. So we needed something like product to embedding, a product title to embedding conversions, some algorithm to do that. So for that, what we did is we used the bilesteam layer from the architecture itself to project each of the product title into an n-dimensional space. So here you can see that every dot that you see, every black dot that you see is actually one of the data points. And the colored ones are actually the ones which are already labeled. So this is how we projected in an n-dimensional space, 200 dimensions to be precise. So next step is we tried a simple k-mean clustering for this. Now I understand people here would think of the dimensionality curves. If you are doing k-means clustering with 200 dimension, it can be poor clusters because, well, it's very hard to cluster in so many dimensions. So, but the problem is we were not looking for very precise cluster. We were looking for loose clusters because we had to just pick up samples from each cluster anyway to get them manually labeled. This was an auxiliary model which was helping our deep sequence models. So that's what we did. We did a simple k-mean clusters. We got a few clusters. Now next step is simple. We had to pick a few samples from each cluster which would aggregate to a certain number. So for example, 1,000 for each iteration. So, and the algo to pick it up was very straightforward. We just used so it was proportional to the strength, the population of data points in a given cluster, and inversely proportional to the data points which are already labeled in that cluster. So, for example, you can see from the last cluster, you'll pick most of the data points to train your model. And this is the complete ADAM training pipeline. Right from the first block describes weak labeling, second block describes the neural network model that we were talking about, and the third block describes active learning. So this whole process was iterated for 4 to 5 iterations at least, and then we have some fruitful results that you can see here. So here in the results, you can see most of the products here are very different to each other. For example, the first one is from, it's a fruity jelly, but it's actually a kind of candy. The second one, I don't know what that. It's, I think, from pharmaceuticals. The third and fourth are from a cosmetic department, apparently. Yeah. So, and then there were many unpopular products here. And you can see that the model was actually, could scale in that one enormous FMCG segment that we were working on. And here are some not so positive results. So we don't claim that we reached 95% or 100% accuracy because, trust me, our data is horrible. And so there were some very uncommon sequences that were present, and the model couldn't scale on them. It was very hard for the model to predict on them. So yeah. Now here are some matrices. I can better explain this with the graph. So the orange line here you see is the improvement in complete sequence matching accuracy, which started from only 22%, and it reached around 77%. And I haven't included the results from last iteration, and in that it actually reached 82%. The final accuracy for complete sequence match was 82%. And for individual accuracies, like for brand and categories, it actually started from 0.4 and 0.39 respectively, and it actually reached to 89 and 86%. So these were the highest level of scores that we were able to reach with only 4 iterations. And at every iteration, we only took 1,000 new samples. So with 8,000 previous weak label data and only 4,000 new samples, we were able to achieve this massive jumps and higher accuracy. The last line here actually you see is the baseline traditional CRF model. We put it there to compare with the model, and you can see that the model couldn't scale with the variance that we had. So these are the proof that a deep sequence model can actually generalize much better, because the first layer, the embedding layer, you don't actually create any handcrafted features. You extract them based on the context where the words are present. So that's why it was able to scale on so many different products. So here is our contribution. We proposed a novel entity extraction model for domain-specific data. There's nothing that hasn't been done before, but to this extent, with so much variance in your data, this was the first time that it has been done. And then our models were built upon many state-of-the-art deep learning and CRF models. And then it further leverages weak labeling and active learning. So there were 3 crucial components that came all together to achieve these results. And the extrinsic sampling technique that we described earlier was actually novel. This was the first time that something like this was tried. So these were the main contributions from us. Here are the key takeaways. Deep neural networks are the buzz right now. You can see them everywhere. It's actually almost a solved problem for autonomous driving. There are products out there. But it still hadn't made quite the cut for NLP. It's because the problem with the label data, the data that we have in our industry grade is so much poor compared to the data that people experiment on in labs and for research purpose. So that's what we try to show here. We showed how you can make an industrial grade information extraction module. So that is our key takeaway. Another key takeaway would be, so active learning is a very fairly newer research now. So I believe that it can be very important concept in industrial domain, in a real world scenario, because yeah, trust me, the data that you see in real world scenario is far worse compared to what you actually see in research labs. So yeah, that's another key takeaway. Now here is some future scope for Adam. Now currently we are working on extracting higher order attributes. Now, for example, in the first example, you see that ideally, currently, Adam would pick Goodnight and Advance as the brand name. Goodnight Advance as the brand name. But at higher level, we know that Goodnight is actually the base category and Advance is some base brand, and Advance is one of the variant of that. So that's what we are trying to predict. That's what we are trying to further divide these extraction information. Similarly for categories. So in the second example, you can see that cookies are actually base category and cashew and nuts are flavors or ingredient. I don't know. And then we are trying to scale across different segments like FMCD. Now we are currently working on FMCD department. And we'll apply similar approach to that also. And then there are other segments also like automobiles or hardware, etc. Pharma maybe. So yeah, these are the papers and inspirations that we got that. I would especially thank my teammates Abhishek, Deepak, and Ashish to help me achieve the results that we achieved. Ashish and Deepak were great mentors, and Abhishek was a nice teammate to have. And then then I would also like to thank Data Ops team. So Data Ops team were the one who actually did all the manual labeling work for us. So yeah, a big thanks to them. Yeah, that's it. Thank you. Any questions? Sorry. Yeah. Yeah, you.
Spacey. Hello. Yeah. So Spacey also has NER model.
Sure.
Did you benchmark it with Spacey? And what I've found that they have moved from BiLSTM to convolutional layers. So have you tried convolutional layers solvers?
Yeah, I mean, I understand your point. And there is one experiment that is going on with convolutional layer. We are not using Spacey exactly, we are using PyTorch, but the algorithm is same. And the results were very similar to that. So we didn't move with CNN layer. See, the problem with them is CNN layer is, again, you cannot train it in an unsupervised way. CNN layer comes at very starting with characters. So the what problem that occur if you have very less amount of label data, it would massively overfit to that domain. So you cannot move with, so that's why our first layer, the embedding layer that I was talking about, was an unsupervised, it was trained in an unsupervised way, and it was a frozen layer when we moved with the architecture. So with CNN, again, so if you used any complicated structure in the first, the problem is, again, you need a large amount of label data, and you wouldn't be able to, it would massively overfit, as I was saying. So that's why we didn't try, because we are working with CNN layer for character embeddings also. So we are working with similar algorithms, but it shows this was the only approach, the simpler one module, which was actually able to scale better than compared to them. I hope that answers your question. Anyone else? Yeah.
Hi. So the thing is that in the whole active learning system that you have developed, is there any framework for doing this, or you built it yourself?
We actually built it ourselves. There is, so we don't need any we needed one framework for the labeling part actually. So we actually created in-house, but there are tools like SageMaker from Amazon, and it cost a lot actually. And when we started this, it was an experiment. We didn't know that it might succeed this well, so
you
we
mean
started with an in-house way.
So the SageMaker has an active learning module.
It's so they have an annotation system for annotation module for you where you can go and manually label. So you can fit your algorithm. You can change the algorithm of sampling there. You can fit it with their framework. You can fit your whole data. I mean, they can read and write data set from S3. So yeah, you can make that module for active learning. You can customize it for active learning.
Okay.
So
another thing
Hi,
that excuse me.
can you take it offline so that if someone else has a question?
I have a different question actually. Okay, fine.
well, no problem. We'll discuss.
It is about the k-means model. Actually, I'm also working on active learning, so that is why
Sure, we can
can
discuss
talk.
about it. No problem.
Okay.
Anyone else? Yeah.
Thanks. So it was really very nice talk.
Thank you.
Specifically like the active learning part of it. Just
Thank you.
one question maybe I missed in the start. So the accuracies that you were calculating, so those were with respect to the weak labels that you created, or were those with the actual labels that you had 8K samples?
No. So they were. So we had a separate holdout set where we calculated the accuracy. They were manually labeled. They weren't. Yeah. So we calculated all these accuracies on that, and also those holdout set were pessimistic. So all the brands and categories which were present in the holdout set, we made sure that they weren't present while training, so that we can get actual real-world scenario numbers.
Yeah. The reason why I asked is because that would have been a very big covariate shift in terms
True.
of the real-world use case.
Yeah. So that's why we had a separate holdout set. It was never used anywhere else, and it was manually labeled.
Cool. Thanks. Man.
No problem. Anyone else?
After the k-means algorithm that you used, do you have any idea how many clusters were actually not mapped at all, where you probably did not take any words for probably manual labeling?
Exactly, I didn't have any idea about it because I wasn't bothering about it initially. I thought eventually it will get picked up. But yeah, there were some numbers of a few clusters which were never. So because I was picking numbers from every cluster, or any cluster which is of significant amount you would definitely get samples picked up from them. Your algorithm works that way. Only there were some few left out clusters which had very less population in them because your clustering algorithm was proportional to it. So I wasn't worrying that much about that initially.
Because it would lead to the long tail of
Yeah, I understand your
Yeah.
point. But uh, the problem is those clusters which are getting left out and you won't actually train on them. What will happen is because the amount of data there present there is so low that initially I wasn't worrying about. See, I was talking about iterative data that will get right. Eventually, what would happen that it might be possible those clusters get increase in number. So what will happen? Your active learning will automatically take care of it. Your approach would automatically take care of it. Anyone else? Yeah.
Okay, since we have time, so other thing is that in terms of k-means clustering approach that you're using, the purity of each cluster is something that affects your
True.
labeling process.
Yeah.
So have you tried any other approach?
Yeah, we there was two approaches. One was intrinsic sampling, where we use the model itself to check how the confidence score for any output. We ran it on all the unlabeled data set that we had, and then we see whether the confidence score that is generated by the model is very low, irrespective of what the output is. If it is very low, it means that model is unstable for that. But the problem with that was the scores that we were getting was very random because in starting of the model it was very different. That's why we couldn't use that.
Currently, I'm working on a hierarchical sampling approach for
Okay.
this, so we can discuss that.
Sure, no problem, man. Yeah. Anyone else? All right. Okay. Thank you. Thank you for your time.
Thank you, Sandeep, for the wonderful presentation.
Shashank.
Oh, so Shashank. And next, I call upon Sandeep Kurana. He's a research scholar and a data scientist at ISB to talk on the topic core concepts in social network analysis. Welcome, Sandeep.
So welcome everyone. Am I audible at the back and too loud, too low, or is it okay? Okay. Social networks, firstly, I mean, good thing, bad thing. It is not a new thing for us. In fact, many of us have been through the evolutionary cycle of being enamored by them, the craze of joining, adding friends, and many of us in recent times have even quit social networks. So where do you all stand? And yeah, one important thing, it is not just that you have to be on social network. There is a lot of literature coming up, a lot of popular books now in the power of introverts. So you need not feel that if you are not on a social network, you are getting left out. You should read books by Susan Cain, that is about the power of introverts, and also Deep Work by Cal Newport, both of whom say that to do something really deep and meaningful, you may possibly have to remove these distractions or remove this information overload or the relationship overload, and then the introverts do have their own power. So no matter which end of the spectrum or where in between or where in your own personal, say, personality development life cycle or social media presence or absence life cycle where you stand, that by itself will not be an indicator of your success or failure. But more important to be yourself. That is what everyone, all these experts would say. That as long as you are your natural self, whether you are on introvert side or extrovert side, and there are a lot of myths also around the introverts that they don't mix around, but the reality is that they have their own preferences and ways of meeting people, and they have their own, say, few but more deep relationships. So both kind of say personality types are good. There is nothing wrong with either of them. But this talk is not even about that. This talk is about everyone in front, which means whether it is an introvert, whether it is an extrovert, whether it is heavily extroverted or mildly extroverted, someone on social media, not on social media. It is very difficult to escape networks. It is very difficult, even if you are not embedded in a network, to not be influenced by it. So this talk is not about your presence or absence on the network, but this talk is about under the hood what happens. When you are or are not on the network, then what you can do using analysis to make certain inferences. How many of you have been introduced to the subject of social network analysis? Please raise your hand if you have been introduced to the subject. So good. Then my talk is tailored appropriately, except I think I saw only 2 hands. Rest of you are pretty new to social network analysis. So I'll try and motivate the talk first. In session 1, I'll give you some interesting examples where you see the power of social network analysis. The world is getting more complex. The networks are increasingly there everywhere. And it is important that you understand the power and also the danger of social networks through the lens of social network analysis. So that is in section 1, I'll do some motivation for the talk. In section 2, I'll introduce you to the terminology so that after this session, I don't get a bad name that you attended this session but you don't know the basic terms. So I'm pretty sure in the conversations that we are going to have after this session, you all are going to use those terms, and that will set a common benchmark so that you engage with others and you can build on that basic foundation. We'll go a step further in session in the third stage where we'll talk about the basic theoretical concepts. So I being a researcher, so I research on social media, e-commerce and healthcare, and those are the areas of interest. Those are in fact, tomorrow I'll be presenting my research work. It is a build up to that because I want people to be introduced to social media, social network analysis, so that tomorrow when I present my own research work, then the basics are, or the foundation is laid to understand them. So in the third section, we'll talk about some of the concepts and some of the theory around it. And don't worry, it will be kept interesting and easy to relate to. I'll not get into the maths, which is easy. The stuff which is on the internet or Coursera courses, those you can look up there. The maths is the easy part, but more important to get the intuition that what does that concept mean, and then thereafter the rest is either inbuilt formula or you can look it up in the on the internet. In the last section, I'll share some resources which you can look back when you go from here. There is also a quick say introduction to the tool itself. Uh, there are many tools, but I'll just quickly give you a glimpse of one or two tools, whatever time permits. And in case any questions, if it is relevant, you can ask during the talk, or else we can ask them towards the end for any reactions or questions. So networks are there everywhere. In fact, in many places, as you go through the presentation, you will realize in many places you haven't realized that there is a network existing. It is only when someone tells, oh, there is a network possible here as well, that then you realize, oh, that means there are networks here. So where do you see networks? We see them on our telephone contact books. How does that become a network? So if you are Truecaller, if you are WhatsApp, and you have the access to the Android permissions to take the contact list, then what happens? You can aggregate the contact list of 1 to 1 million, 10 million crores of people to then build a huge network. Okay, so that is the telephone network. Telephone companies alone may not be having access to it, but also the app developers who take access to the contact list, they can easily build the network. So, in fact, the security agencies are pretty worried with the amount of network information that someone, an app developer like Truecaller has, which may not be based in India, but it has access to a lot of contact lists of each individual. So, whoever is in my contact list is my contact, and the way a network is structured is there are two people and then there is a connection. So the connection between two of us is that the person is important enough, whether by frequency of calling or by importance in offline relationship, for me to store the phone number of that person in my contact list. So that becomes a possible, say, social network which one can easily build around. In the olden days, we used to have telephone directories, but these days the directories are all in the individual contact list, and to build a directory, someone will have to access them. Internet, again, if you think of the multiple routers and who is accessing through which router, and then dynamic connections, the internet itself is an interconnected network of say devices. So that itself becomes a network. It is not exactly a social network, but a lot of network analysis research draws from the research in the internet or the telecom networks. Social media, of course, we'll see a lot of examples of that, and social media would be all your Facebook, Twitter, Instagram, or what else did I miss out? YouTube, or any other network where you have the relationships in the form of liking someone. So like is a type of relationship. Following someone, it's a type of relationship. Commenting on someone's profile is a type of relationship. Sharing something is a type of relationship. So there can be different relationships, and the network is constructed on very simple, fundamental, basic entity, and that is there are two, say, nodes or two entities, and within those two entities there is a relationship. There can be multiple relationships, and then there can be aggregation of nodes where once they all get connected based on their based on their individual relationships, it forms a network. So social media, there is that is the topic for today, and that is a huge network. Projects, and within projects, a movie is also a project. So those of you who have studied the organization theory, you would know that within organizations, there is something known as a hierarchical organization or a functional organization or a matrix organization. What that means is hierarchical, there is a department, sub-department, and going down further to the individual team and individual. In a In a functional, there is a horizontal, so there is an HR which will cut into the geographical region. So East India and HR, and that will become then a matrix organization. So there is a functional HR, operations, finance, and then there is a hierarchical, which is East zone, so and so state, so and so city, and then there is a matrix where you have a dotted line and this. But what is of our interest is an organization known as a projectized organization. So projectized organization is like we have in the IT company, like we have in the movies. So I am presenting tomorrow some part of my earlier research, which is around how the Bollywood network structure revolves around the movies. So relationship, what is the relationship there? If I and someone else work together in the same movie, then we have a relationship. It is a co-actor relationship or co-producer or co-participant in a